I'm going to I'm going to talk about new ways of teaching science and engineering. And I'll provide sort of two different aspects of this, which is related to two big areas in which I've worked. The first is just looking at the teaching of science and engineering as a science and doing controlled experiments on different ways to teach and measuring student learning. And then the second part is, given the results we see from these kinds of experiments of kind of much more effective ways to teach than what's used in most university classrooms, the next part will be, okay, what have we learned, and at least in this one large experiment that I carried out on trying to change at a large scale how university faculty teach, and at least in this case at these two large public research universities, trying to change how the entire departments teach. And so we've learned a lot of lessons about that. And in my talk today, I'll just touch fairly briefly on a number of different points, but that will leave lots of time at the end for you to probe me with more questions and issues and bring up, because I, things that are particular interest and relevance to you. So the first point is that in the past couple of decades, there's been major advances from three different areas of research, really. The cognitive psychology of people in labs study how people think and learn, and then brain researchers, and the area in which I and many other people work is research in the college science classrooms. And from these three areas, we're now getting pretty clear principles and results on what's involved of learning of complex thinking, like, thinking like a scientist or an engineer. And so I'm going to give you some examples of some of the classroom research that sort of supports this. And I just start out by saying the kind of things being measured here are really giving students certain problems and seeing how well they think about those problems and find solutions, thinking like experts in the subject. So they're not hard problems, but they're easy problems to a physicist or an engineer. But you want to see if the students are developing those same kind of problem-solving skills. So this is one example that was done at, I guess it's Cal Polytech, and they were looking at their big introductory, or moderately big introductory physics course that most of I think all the students take in their first year. This is much the same as a physics course taught in every university in the country, and if not the world. And they look at, there's a carefully developed test developed by physics education researchers that take the basic concepts of force and motion that are covered in this by this class, and then they give students questions to see if they can, simple real-world situations, to see if they can make correct predictions like a physicist would, using these concepts of what's going to happen, when cars run into trucks and balls are rolling off tables, etc. And so using this test, they measure how well the students can do this before they've started the course, and then they look at how much they've learned, how well they've improved by the end of the course. And here, in this study, which is, there are many others that looked at similar things, but they collected data on many instructors over many years, and they found that typically the students would learn about their learning gains, as measured this way, were about 0.3. So that was about, they learned about 0.3 of what was possible and what you'd really like them to achieve. This is a very consistent result for teaching this introductory physics material like this using the traditional lecture approach. That's what I should say. This is a traditional teaching approach. And then what they did across all these different instructors and all these different sections was to adopt this kind of new, what I'll call active learning pedagogies, which I'll explain more in a minute. But when they did that, you can see basically all the instructors went up. On average, the learning by the students just doubled. But the key point here is that these are the same instructors, and they're simply using different methods of teaching, and you're seeing large improvements in student learning. And for example, this instructor, those students are learning a factor of 6 times more than they were when that instructor was just standing up and lecturing to them. And so the point that I want to make of this study and other studies that have been seen consistently in this area is that it's really about the methods the instructor uses to teach. It's not other factors about the teacher, at least at the higher education level. And so you see all of these different instructors, and when they change their teaching methods, their students learn more. And so that's all there is to it. This is a similar example. This is in computer science, work of Beth Simon at University of California at San Diego. And they were measuring the drop and failure rates. And so Beth actually came and worked with me for a year, learned about these different ways of teaching, and then went back and worked with the other 3 instructors who covered this is the core of the computer science program at UC San Diego, the sort of beginning parts here. And what you can see here is then the drop and failure rates dropped for each of these courses, dropped dramatically when they adopted this different kind of instruction. And so on average now, they have about 1/3 the drop in failure rates from these 4 basic courses they used to have. And so again, it's an example of you have the same instructors simply adopting different ways to teaching and getting dramatically better student results. At a place, UC San Diego Computer Science, this is a very large number of students who are now being successful in this program just because the faculty learned how to teach better, essentially. Okay, so those results, and many others I could point to. In fact, I could point to about 1,000 other published results looking at similar comparisons across science and engineering, where you're looking at teaching by various measures, where you're comparing teaching by the traditional lecture approach or teaching by these active learning approaches, but you're looking at an entire course. And so that involves, students coming to class and listening to lectures and going off and studying for exams and doing homework sets and so on. And admittedly, that's really the most important outcomes you care about. But we want to do a very specific experiment, which was to measure just what happened in the classroom and just what happened, the amount of learning in the classroom. And there were a couple of reasons for that target. One was that's most of the faculty spend most of their, when they're thinking about teaching, most of their time thinking about what they're going to do in the classroom. And then the other issue that we want to address is very often when we're talking about these active teaching methods where students are doing much more work in thinking and answering questions in class, people assume you can't cover nearly as much material. And so we wanted to do that, to put that to a direct test. And so, so this was carefully scheduled. So it took, it was the large, at University of British Columbia, the very large introductory physics course that all the engineering, future engineering majors had to take. And so we could take 2 sections of 250 students each, so this is done in a very large class. Measured them very carefully to show that they were virtually identical by, I think we had 7 different methods we used for this. And so the students were the same, but the teaching in the control experiment, it was the standard lecture course. But it was given by someone who was very experienced at teaching this material, and he had high student evaluations. The standard at pretty much every university in North America for evaluating teaching is just the student evaluations that you get at the end of a course. His were very good, and so by the standards of pretty much any, Stanford University or most any other place, he would be considered a good teacher. The other section was taught by somebody who was a new PhD in physics, but he'd been trained through my program in these principles and practices of effective teaching. And so they covered, in this, the 2 instructors, they agreed on exactly the same set of learning objectives to be covered in exactly the same amount of class time, 1 week of lectures. And then right at the end of that, and the students didn't know it was coming, so they didn't do any studying, and the timing was such they weren't doing any studying for exams or problem sets. They were given a test covering those learning objectives to see, okay, how much had they really learned from coming to these lectures. For those of you busy taking pictures of my slides, I'll make my slides available, so they'll be better quality than your pictures probably. So, okay, so here's the results of that, and so this gives the the test score versus the number of students for each of these 2 sections. And I should say, on this particular exam, just random guessing would give you 3, and so you have to sort of think about the amount of learning that students achieved as how far they are above 3. And you can see there's just a profound difference in these distributions, right? That the person giving a standard, the experienced, highly rated teacher giving a standard lecture, the learning is just much, much smaller than in the experimental section. This also demonstrates something that other researchers in this field have shown, which is that these ways of teaching aren't something that just help one part of the student population, the best students or the worst students. You can see this entire distribution has moved up here. So it's really clearly a bit more effective for all of the students in the population. So those are a few of my favorite examples, but as I say, it's kind of funny because there's a lot of research in this area that's been published, but it's really not very widely known and not very widely acted on. And these studies consistently show that these better pedagogies give greater learning, lower failure rates, and they benefit all. There's some indication that the students who are most at risk get somewhat more benefit than the other in the population. And there was a large meta-analysis of several hundred such studies looking across the sciences and engineering published last year by Freeman et al. And they showed how these effects seem to be quite similar, independent of what field of science and engineering one looked at, and also what level of course in it. So it seemed to be quite a, it made a good argument that this is quite a general basic result. And so I'm going to now explain to you, why that isn't surprising at all, why you expect this to be something that's going to hold consistently, and also kind of explain to you what goes into this kind of form of teaching. And this, so the basic underlying theory of this you can relate to the studies from cognitive psychology on the development of expertise. And because all the results are so consistent with this fundamental theory, it also gives one much more confidence that if you look at some new subject or new level or even new student population, you can be pretty confident that it's going to still show the same kind of effects, because we do understand that, we have a solid theoretical framework that works. And so the basic theory here is just that people don't learn to develop kind of thinking capabilities of thinking like engineers or scientists and so on from being told how to do it. They learn this by explicitly practicing the kind of thinking that's required here. And along with that practice, there has to be guiding feedback. So someone has to go review with them how they're, what they've accomplished in that practice and what they can do to improve further. So, I think the best way to think about this is just, it's, very similar to athletic performance, and you think what a good athletic coach does. If they want to, teach people to play basketball, they don't sit and tell them how to play basketball hour after hour after hour. They think about, what are the basic skills that make up success in playing basketball, and design tasks that have the learner, the basketball player, figure out how to practice those tasks, and then they give them feedback on what to do and how to get better. But one of the things that I want to emphasize here is that if you think about, learning physics from this perspective, or pick your mechanical engineering, whatever, you realize that the subject expertise of the teacher is really important, because unless you really understand what it means to think like an expert in a subject, in the same way you have to understand what it means, the skills needed to play basketball effectively, you can't design appropriate practice tasks for the students, and you can't recognize when they're doing better or worse and giving them feedback on how they can improve. And so at one level, I think this is probably the basic justification for the research university, where you try and bring together people who, are both experts in their discipline through doing research in it, and then to also make them the educators and the teachers. And then, so the third aspect, and I think it often gets neglected to effective teaching, is to deal with motivation. Obviously, if you don't know a subject, there's no reason you can see that you should put in the large amounts of intense effort required to master it. And so an effective teacher not only has to worry about the practice tasks and the feedback, but also motivating the students to put in that learning. And so all of these experiments, all the kind of research I'm showing, that's basically what goes into the instruction there. So let me talk a little bit about, and I'll give you a little more detail about how this is applied in the classroom, and I can go into lots more detail later on if people want. But a typical way this would be used in teaching is first, the students would start out by having a targeted reading they have to do before class and some simple little online quiz to make sure they did it and reward them for it. And what this is doing is this is simply taking the simple information transfer and not wasting class time with it. You know, there's no reason to have an expensive faculty member be nothing but essentially a talking textbook. That's a very poor use of resources. So, you know, the students do some basic reading, get some basic information. It's important to realize that that doesn't mean they really master the material, but they've got a starting point. And then in class, instead of sitting listening to information, they're actually given questions or tasks that they have to solve and figure out. And so, and these tasks are then carefully designed by the instructor so that they're really practicing the particular components of science and engineering expertise you want them to learn. And I'll give you some examples of sort of generic examples of this, is that in every area of science and engineering, they have a certain set of conceptual mental models that they use, and they've got criteria for deciding when that, you know, given a new problem, a new context, whether that, which of those models is useful or not for solving problems in that case. They have these complex pattern recognition systems for deciding what information is needed to solve a problem and what's irrelevant, and so they can sort of simplify and organize the problem. And when they reach, you know, they have some conclusion or result, they have any specific to the discipline, they have a set of criteria by which they judge if these things may, you know, if this makes sense or if I need to go back and modify and rethink this problem. And so there's various other things as well, of course. And so none of these talk about knowledge or the particular subject, but it's important just to recognize that, of course, they have to have knowledge about the subject, but the meaningful learning is to learn that knowledge, that information integrated in with these sort of more general thinking skills in the subject. And so they not just have knowledge, but they understand when and how to use that knowledge effectively. And we have lots of research where people see that students can learn a bunch of information, but never, you know, from their courses, and then never be able to use that information effectively when they're given real problems. They're only able to use it when they're given some exam question. Okay, so just to continue what's happening in the classroom. So they're given these questions or problems to solve, and the way this might work, especially in a large classroom like this, and the examples I showed, is that the students would be posed with some question. They need to have some way that they can respond, and that so that they have to think about it and be committing to some kind of answer, and that the instructor can see what the different students are thinking, and so guide what they do accordingly. And so in the kind of examples I showed you, and the typical research in this is that the students will have these clickers or personal response systems, so they can push a button when posed with a question, they push a button and the instructor can see, okay, who's thinking about this right, who understands it, who doesn't, fairly quickly. But also it just, again, makes the students have to do the kind of thinking that when you're committing to an answer that someone's going to look at, you do a very different thing than if someone just says, what do you think the answer is going to be? And you just sleep through it, right? So they answer questions that way, and then they'll be discussing. In this case, they're working with a worksheet where they have to, you know, write things out, working in small groups like this. And while they're doing any of these things in small groups, the instructor, which is like this, is circulating around, listening in on those conversations, spending most of the time listening, understanding what students are having trouble with, what they're clear about, and every once in a while, making brief little interventions to, when students have some special small problem, they can fix it and move on. But then at the end of this kind of activity, which might be 5 minutes or so of students working together, then the instructor will have a follow-up discussion. And so that will be bringing together all of the ideas that have picked up in listening to this, all the student questions that have been generated, and covering, again, sort of looking at what aspects they're thinking in the desired way, where they're going wrong, and how they can improve that. And so in this case, I mean, sometimes when people talk about this active learning, or they call it student-centered and so on, which I'm not crazy about that term, people think it's you're turning the learning over to the students. That's not true at all. In a classroom like this, the students are doing, spending their time working on problems that are carefully designed by the instructor, and then the instructor is still spending a large fraction of the time. In classrooms we look at, it's typically 50–60% of the time is the instructor talking, but it's follow-up discussion. It's targeting the specific things the students need. It's not just telling them information that they have no idea of why they want it, okay? And then, as I mentioned before, these kind of activities and tasks and the follow-up also need to make sure they connect up with students' prior knowledge, and so they're building on it, and also building on motivating the students to put in the work, desired effort. So these kind of teaching methods have, like I say, have been used across science and engineering. I don't think people have looked too much at the cost, except at the work that I've done at Colorado and University of British Columbia. We did look pretty carefully, and we see that once people have adopted them, there's no additional cost. They cost the same thing, the same instructional cost. They just produce much better learning outcomes. So given this, why isn't everybody teaching this? Why is it that you can walk across this campus and maybe one classroom out of 20 will actually have people teaching this way in it, okay? And this is actually related. I saw that you were going and looking at, I think, told you were going around to visit Stanford and Harvard and Olin College as kind of models of education, and it's closely related to why I think those are very poor models for you to actually be looking at. So I'll just put in a warning there. I'll get to that. So, but the answer to this question really takes me to the second half of my talk and the second, perspective that I come from. So this is really looking at institutional change and why institutions and faculty behave the way they do, and what's needed to get better adoption of these teaching methods, okay? And so this is really these science education initiatives I ran at these two institutions, targeting the teaching of across entire science departments. And so the first basic answer to this question of why they're not being widely used is it's basically the official incentive system that the faculty and the administrators and the departments are actually doing exactly what the incentive system is rewarding them for doing. And what that is that I know certainly in North America at basically every university, I'll just make a flat, confident statement that really the only thing that there's any meaningful measurement of is the research productivity. And it's measured for faculty, and it's measured for departments, and it's measured for institutions, and there's all kinds of rewards that go along with enhancing that productivity. Now, there's some great value to that. I'm a strong believer in science research, after all. And it's, research universities have been enormously powerful, beneficial institutions for society. The problem is on the only, because that means nothing else matters, right? And so the teaching is basically, there's no meaningful data collected on the teaching and the effectiveness of teaching. And so, and I did a poll of the major university organizations in, I guess in all of North America, really. And there's no institution that collects data on what teaching methods are actually being used by their faculty in the classrooms. Even though we have this great body of data saying that, you know, you have dramatic differences in the effectiveness between the two methods, nobody's even bothering to look at which is being used. So, you know, I like to sort of point out this is kind of analogous to if you have a hospital and you know that, well, some of the doctors are, you know, using antibiotics to treat patients, and some of the doctors are just, you know, using bloodletting, and the hospital saying, well, it's up to the doctors. We're not going to bother to look at who's doing what. And so if you've got no meaningful data on educational quality, then the only thing people have to go on with universities is their research prominence. And so that has become this sort of misguided proxy for educational quality. Now, and what this means is the institutions that are the best in research and have the most money to throw at it are seen to be the best educational places. And so Harvard and Stanford fall very clearly into that category. And as a result, they get the best or most favored students end up going to those institutions. If you start out with wonderful students, you know, very highly prepared, very highly motivated, it's pretty hard not to have them be successful no matter what you do. And so, so this sort of reinforces this whole kind of erroneous judgment. And, but, you know, for a group like you, which are thinking about how you're going to design a good educational institution, yeah, it'd probably work fine if you could take Stanford or Harvard and simply move them down to Brazil. But you're not going to be able to, you know, if you think you're going to build something down there that looks like that and have them be educationally effective, you're mistaken. Okay, so and I'll just really pick on Stanford here because in fact, just within the last few weeks, I've had a funny situation of a lot of discussions with Stanford faculty in the sciences and engineering about teaching and ideas about teaching and what they're doing. And I've also had meetings with Foothill Community, you know, it's a 2-year community college just down the road there, and then San Francisco State University, which is a state university system, so that's sort of the lower tier of the public universities in California. And there's just a profound difference. At these institutions, you talk with the faculty, you talk to them about what they know about teaching, what methods they're using, what they're doing to try and measure the student success and figure out what to do better. And it's just profoundly different from what you get if you look at Stanford, either as a faculty or an institution. So I would actually make quite a confident prediction that if you took, for example, all the Stanford students and you switched them with all the San Francisco State students, the Stanford students would probably do better than they are now. And the San Francisco State students, it'd be a disaster having them taught by Stanford faculty because they just wouldn't know what they were doing. And the point is, at those kind of levels of institutions where you're not able to select students who are sort of guaranteed to be successful, there it matters much more how effective you are, what kind of data you look at, and you take advantage of making sure you understand what students' preparation is and what they need. Okay, so that's ranting about Stanford. I do know some about Harvard. I've done some consulting there, and they're not really that much, they're pretty similar to Stanford in this regard. And if you want to look at Olin College, frankly, Olin College is a ridiculous model that to think you could scale up. And I never imagined anybody would even suggest that until, to be blunt, and this, I say this because I kind of get offended at what they do, I realized the claim that they could be scaled up and other people could use this is really part of their fundraising message, that they get people to donate the money because they're saying, oh, we're going to be a model for how Brazil can teach, whereas it just, you look at the details of the financial structure and selection, it's just completely unrealistic. Okay, so I'm gonna finish up here with some, I'm now telling you what to do in your universities, in your country, and in your culture, and so I recognize this is highly speculative and you shouldn't take it too seriously, but I want to just throw out, certainly in STEM, and we could debate how far it goes into other disciplines, but certainly in science and engineering, the research says that what really counts is the teaching methods the faculty are using, and so you should start measuring what those teaching methods are and rewarding and supporting faculty to learn them. And so I'll talk a little bit how to measure it, but obviously you can't measure something in the faculty and say you should get better at this without providing resources and support for doing that. And so this is where my experience with the science education initiatives comes in, because that's what we were really figuring out how to do. And I'm going to make a very tentative claim here that working, and I'll show you, we've now transformed the teaching of about 300 faculty across many different departments, and very roughly it sort of takes about 50 hours of faculty training time to learn how to use these methods in a reasonably effective way. So when I told you it didn't cost any additional for the instruction, that's after people are trained. You've got to figure there's a startup cost of getting them to know how to do this. And in this training, what it really requires, and you have to really think about the teaching from this perspective, is that you have to, it's not enough to just be experts in the content, but you do have to have your teachers be experts in the content. And so, but on top of that, you have to have them be experts in the teaching of how do you effectively, teach that content and help and support students' learning. And so that's really what your training is involved, is bridging those. Getting back to how are you going to measure the teaching method. So this is something that we worked on and put a lot of, actually, a serious effort in developing for these science education initiatives, because we wanted to be able to measure if we were making a difference. And so I'll just give you some references. You can go read about all the details behind the design and the principles of this on just this better way to evaluate undergraduate teaching. But then we have this tool that we developed specifically for being able to characterize the teaching goes on, and this is this teaching practices inventory. And to develop this was actually a pretty major effort. This was about a 3-year project of many iterations to get something that could be quite quick and straightforward for faculty to be able to fill out. So it only takes 10 to 15 minutes for a faculty member to complete this for their course. It's very objective, so it's just kind of checking off whether they do things or whether they have something or not. You can check if they're right, but there's not really much problem with that. But this gives you then a very detailed characterization of how a course is taught, and really all the different areas in which how a faculty member, the decisions they make, in how they do grading, what they do in class, what kind of materials they provide to the students, homework, etc. And so in the end, it gives you, if nothing else, just a far more detailed, clear picture of what the instruction is like. But then what we do is so once they've filled this out, we can go through and look at all these different details of how course is taught. And we've gone to the research and said, okay, which of these things do we have solid research saying if you do this, students learn more, and we give corresponding effective teaching points for that, and then you sum over everything a person does in their teaching, and you can come up with an effective teaching praxis score for an entire course. And so when we've collected this kind of data, these are across the science and math department at UBC, these are the kind of the range of scores that they see for their different faculties. So this is 50 is a very good score. Here, 10 is not a very good score. It means they use almost no practices that have shown to be effective for learning. And so this is just to show you that we have a tool that certainly can measure differences across faculty that's pretty easy to use. I'll also point out that, every single one of these departments, when they collect this information, this was completely new to them. They had no idea there were these kind of differences going on because they and no other institution I know of has actually looked at this kind of level of information. This is just to show you, it also can tell you very clearly if you're actually improving. This is one of our departments that made a serious effort to improve their teaching methods, and as reflected in these teaching praxis scores, you can see there that distribution moved way up. So I'll just finish with a little data. I don't want to go into details about the Science Education Initiative, but this is just to show that it was to see if it's possible to get large fractions of science faculty, research active faculty, to change how they're teaching. And so this really proved that it was. In the most successful departments here, we've seen around 90% of the faculty have substantially changed their teaching to adopt these effective research-based methods, and a similar fraction of the student credit hours are now being taught using these better methods. And so, and this is up to pretty high scale now. It's about 140,000 credit hours in science at UBC a year. That's the great majority of what they teach. So this is really shows you, yes, it is possible to transform. Okay, I'm going to just say a couple of very quick things, and then I'll stop here. On just some side notes on some things that I've looked at and looked at research on. There's a lot, you hear a lot of talk about the great solutions that, well, you just need these wonderfully designed classrooms and that's going to solve all your problems, or you can bring in technology and that's going to make everything wonderful. And so a quick summary of what the research says on that is that looking at kind of the optimized, what people see as the optimized classroom, it has small classes, got movable tables and chairs. What do we know about that? So first, these studies that I referred to on these optimized pedagogies versus lectures, they've been carried out over very large numbers of courses of different size and different types of classrooms. I showed you some that were done in 250-seat lecture theaters and 40-student classrooms. And what one sees is that in the comparison versus the standard lecture across that range, you typically get something like an improvement in 1.5 to 3 in your measures of learning. If you then say, okay, let's take the best teaching methods and compare them in a big classroom, big lecture theater, with a small optimized class, how much improvement is that, because that's really the cost-benefit analysis you have to do if you're running a university and you're spending money because these things are expensive, okay? There's one small study, I mean, it was a good study, but it's a small study done at University of Minnesota when they really had optimized pedagogy in both places. There, the improvement was about 10% for the smaller optimized classroom compared to the large room. So yes, that's not a trivial improvement, but it's not nearly the return on your investment you'll get from simply changing to be good pedagogy no matter what classroom environment you have. On the subject of educational technology, I think probably you all know this, but I'll just put it in there. I mean, the big danger with educational technology is people get some technology and they say, oh, this is a wonderful technology. We're going to run out and use this. And there's lots and lots of examples where it just doesn't really work, Having students watch lectures online as opposed to coming to class, they're both pretty worthless, right? And so but at the same time, there is a tremendous opportunity for use of technology, and you just have to think about the principles I talked about of what makes up effective learning, this practice, the appropriate thinking, and getting targeted guiding feedback on it. Technology can really help that in that, particularly in larger classes, it can extend the instructor's capabilities. And so in like the examples I show where I can be teaching 250 students and I can find out right away, posing a question to all of them and seeing what they're answering there, and then judge what I do accordingly. And there's various online interactions I can use, and so on. And so the real idea here is that you need to think of the technology as a way to enhance communication. So not testing, but really enhance communication, because the communication plays such an important role in this. And so there's lots of ways it can be done on this, with really the emphasis on the feedback of giving the instructor the capabilities to be more informed and more targeted and more effective in their feedback because they have technology. And then there's some other novel things we have, instructional capabilities. There's something I started many years ago that's now gone off and been very successful without me, of these online interactive simulations that allow people to essentially build in the conceptual models of the science, and students play with it, interact, and it's a completely different medium. It allows students to interact in novel ways and visualize things in novel ways, and it's being used now about 100 million times a year. And I think actually Brazil is one of the biggest users of these PhET simulations outside the US. And so that's just an example of a particular technology that gives particular useful capabilities. Okay, so then I'll stop, and we have some time for questions and discussion. That I think, this taking this more scientific approach to teaching has the potential for really tremendous improvements, but then there's issues about how to change the culture to have it become the norm. Thank you.